share my screen. Okay. You can view my screen, right?
Yes, you're good.
Okay. Hi, everyone. My name is Samrat Acharya. Today, I'll talk about demand-side cybersecurity of smart grids. This project was done with PI Dr. Ramesh Curry and Dr. UDT working, and it is funded by NSF, NYU Center for Cybersecurity, and NYU CASP, with the Center for Urban Science and Progress. So, moving into the content, right? So, power grids conventionally, or even today, uh, have generator facility at one end, and the generated power is transmitted by long transmission lines to the distribution transformers, and these distribution transformers distribute the power to the individual customers. So all of this power flow scheme is controlled by a centralized controller called SCADA. And the good thing about this architecture is like we can have an industry grade defense in centralized controller, they call SCADA. Even in this architecture, we have already seen cyber attacks. The prominent example of this is 2015 Ukraine power grid attack, where the attackers sent spear phishing emails to the employees working in SCADA, and they got access to the SCADA computers, and the attackers managed to switch off some of the uh, distribution transformers. So as a result of that, more than 225,000 customers were left out without electricity. So, but these days, the power grid has a paradigm shift. So having said that, the generation facility right now no more is not only the entity who serves power to the customers, rather we have like bidirectional power flow. That means in the customer side are no more customers, they are prosumers which can generate electricity and consume electricity. So that is done through solar panels, EV charging and all. So on top of the centralized SCADA controllers, we have deregulated and decentralized customers called IoT devices at customers end. And we know that like the IoT devices are growing in numbers. Today they are around like 31 billions, and within like 4 or 5 years, they are expected to grow by more than two folds. And all of having IoT devices and customers in, now we are handing the cyber security aspect to the customers hygiene, right? So we have already seen large scale attacks by IoT devices in 2016 called Mirai botnet, where like the security cameras using default passwords were hacked, and those compromised cameras were used to congest the DNS server. So fortunately, till the date, we have not seen any attacks on power system using those IoT devices, but we cannot deny the fact with the increasing number of IoT devices. So today, my presentation will focus on uh, two schemes. Basically, one attack vector is EV charging facilitated by public data, and another is the process in smart grid that is called demand response facilitated with artificial intelligence, right? So let's first talk about EV charging. Uh, so why attackers target is EV charging? Because the very first reason is EV number of EVs are increasing rapidly. If you see through 2010 to 2019, it's an exponential increase, and this trend is increasing further, right? So on the right hand side, if you see, these are the red dots are the charging stations only of Tesla in US and Europe, and they're already dense, right? So the second reason to this is like we have growing capacity of electric vehicles and charging stations. For a few years back, we have like charging stations less than 3 kilowatt, but we have already 350 kilowatt charging stations, which can charge modern electric vehicles less than in an hour, right? Half an hour. So also in the vehicle side, we have already the battery capacity that's more than 100 kilowatt hour, which gives like hundreds of miles of range. And all of these EV charging is being facilitated with like internet enabled charging. So due to these three causes, these three reasons, we have increased cyberspace, and the wattage of the power capacity in the EV charging is increasing. So let's look at the cyber physical outlook of EV charging, how it looks. Although the figure is a bit unclear, let me try to make it, put it simple. Okay, so I have basically two layers: physical layer on the very bottom and cyber layer on the top. Within the cyber layer, I have external layer and internal layer. So um, on the left hand side of the figure, I have electric vehicle, then electric vehicle charging station, then power grid. They are connected physically and they are connected in the internet space. So all of these, despite all of this internet space of power grid, electric vehicle charging stations, and electric vehicle, today I'm going to get focused on one of the link, that is electric vehicle charging station is controlled by electric vehicle charging station servers. So these servers control the electric vehicle charging that is connected within its network, and it collects all of the EV charging data, and it broadcasts that data to the third parties, and also it can directly disseminate those data to the smartphone of the EV users, right? And EV users come back to charge to the charging station. So in this link, we have third parties, unregulated third parties here, and also on overall we can see that like the charging standards are not mature enough. So for example, the charging station right now, the communication link between charging station and charging station servers is done by OCPP protocol, but this is not like mandatory and standard, right? They follow different standards. Some even do not follow any standards, right? So we have unregulated third parties, and then like data is public in the system. So I'll try to frame how this public data and EV charging can pose threat to the power grids, smart grids, I would say. So the very first stage called data acquisition stage, we have charging station and electric vehicles. The charging station and electric vehicles data can be easily collected using smartphone apps, as I discussed earlier. And the grid data, public grid data can also be acquired, which I will discuss in a few minutes. So having those data, these data can be now used to create the grid configuration and how the EBCS demand actually looks like, and the attacker might prepare or like better prepare for the attack and launch the attack. So here's the slide how that like attacker can collect public EV charging data. This is a case of Manhattan, where the charging station data are collected using the charging station app or third-party app. And note that this third-party app called like ChargePoint, for example, ChargePoint, they are already found vulnerable, right? So using this sort of charging station app, uh, we managed to find out the all of the locations and then the power capacities of the charging stations in Manhattan, and we could create like what is the individual and average profile of charging like charging demand within that area, right? So similarly for the power grid data, we could able to reconstruct the power grid configuration in Manhattan. So we used Google Maps to locate like the substations and some of the lengths of the lengths between the substations. And also importantly, we use like US EIA, Energy Information Administration data, which gives the location of the power plants, bigger power plants, substations, and the transmission lines. All of these data are public. And also we looked at some of the public documents of the local electricity authority here in Manhattan, Con Edison, and New York ISO, right? So having grid layout and the charging stations data in the figure, let me recall, the red lines are the transmission lines, and the blue dots are the EV charging stations. They are plotted against their capacity. So bigger dots means bigger capacity. And the power plants, there is one power plant in Manhattan, a bigger power plant. And this all grid layout is converted to a engineering layout of the power grid. And this layout now is modeled using the mathematical equations. Firstly, I used like DC power flow equations. I don't want to go deeper into the mathematics here. I model power grid with DC power flow equations. I model generator and turbine. I also model the nodal power demand, which says like there should be a balance between generation and demand at every nodes of the power system. So having all of these equations, we could finally transform this power grid model into a LTI system. Um, so this LTI system is used for a feedback system here. I should say the A, B, and P bar L block. All of these blocks data are generated using the public domain, and they are found using the public data. So the attacker's motive here uh, is to find the optimal value of the charging station demand that need to be manipulated to create some instability in the power grid. So just to note that the P bar L is the nominal charging station demand. Delta P bar L is the change in demand that needs to be done in the charging station, or the charging stations amount of charging station that needs to be compromised, right? So uh, in this scenario, we used SPlane to find out the instability of the power grid. By instability here, we can infer frequency instability or voltage instability. So here, all we know that like in the S-plane, the left half plane of the S-plane, as far as the eigenvalues of the system lies in the left half plane, the system is stable, and when it lies in the right half plane, the system goes unstable, right? So the target of an attacker here is to make the system unstable. That means move the eigenvalues of the power grid to the right hand side. And the attacker here could do so by using thousands of modern electric vehicles that are simultaneously charging with 350 kilowatt charging stations. If they are manipulated at once, we could see the frequency instability or voltage instability in the system. But the attacker can reduce the search space. For example, in the gray region, uh, attackers might not need to go to the complete right half plane. Uh, the NERC, North American Electric Reliability, defines the region of vulnerability even within the left half plane. So even within some proximity of the left half plane, the system gets vulnerable, right? System gets unstable. So the search space gets reduced, and then uh, we can the attackers may only use like 720 electric vehicles that are simultaneously charging with 350 kilowatt chargers, and the systems in the Manhattan gets unstable, frequency or voltage unstable, right? So here at this point we inferred that like there are vulnerabilities in charging stations type of demand, charging stations, right? Or like the electric vehicles. So now for the demand side, we do not have only charging stations. Let's now focus on like the different types of devices, for example, charging stations and air conditioners at home, right? How those devices can be leveraged to make an attack in the power grid. So in this presentation, I'll focus on the process level called demand response. So let me say demand response is a process that is used by the utility to shape its peak demand. For example, let's say tomorrow 2 p.m. the utility projects that we have a peak demand. The utility has two options now. At 2 p.m. Tomorrow, it needs to either switch an emergency generator, or it has an option to ask some of the customers to reduce their electricity consumption. For example, turn off their air conditioners or lower their air conditioner consumption, right? So this asking electricity customers to shape the electricity demand is called demand response. So in the figure, we have a typical representation of demand response, where on the top side I have ISO market, which is typically the electricity market on the transmission level. We have the utility SCADA, and on the lower side, on the middle side, we have the utility DRAs and third-party DRAs. DRAs stands for demand response automated server, and on the lower side we have customers, right? So how demand response works is like the process number one is it collects the schedules. Demand response automated server collects the schedules from the ISO market or via SCADA system. Also, it takes the energy usage data from the smart meters of the customers, and using those power system schedules and the smart meter data, utility DRS produces the demand response schedules. They can use either artificial intelligence or they can do it statically, but increase of like using artificial intelligence is uh, more like happening or like more of research these days. And some of the aggregators or like utility have been started to use it. And also the demand response can happen without aggregators or aggregators. The blue lines are like the process through aggregators. The utility, instead of going and engaging through every customers, it can ask the third party aggregator to bid for certain amount of demand response, and aggregator deals with the customers, right? So here we have a lot of vulnerable points. For example, the smart meters, they have already been um, um, processed for like vulnerability. And also we have smartphone apps in between. So once the utility DRS gets the schedule from utility and the customers, it processes for the DRS schedules, and it sends the schedules to the customers either directly or through the smartphone app, and the customer can uh, deny or like accept the demand response call through the smartphone app, or like it can use some in-home display, the building energy management system, and it can automate the process, right? So this process is standardized by Open ADR protocol, but most of the utility have like different protocol, and they are not, this Open ADR protocol is not unique. And the more of that, like the third party aggregators are not like, um, it's not mandatory to use in the third party aggregators. They can use any protocols here. So there are a lot of like the vulnerable points in this process. So uh, at this end, I would like to uh, explore a vulnerability in the process of like learning the demand response, right? So we have demand response customers on the left side, and we have utility or aggregator, which can be anything or both, in the right hand side. So the customers smart meter data is acquired by the utility or aggregator, and using those historical data, it can it can use some optimization algorithm to design the what is the incentive that I need to give to the customers for participating in that demand response, called lambda t, right? So this is and the process goes on. So in this architecture, the attacker can be place itself in the man in the middle attack. So for example, uh, it can send a false price, that is a different lambda t, um, to the customers, and obviously with different lambda t, as the power reduction of the customers is the function of lambda t, it gets it the power, the customers uh, behave differently, or like turn off or turn on their devices differently. So which will create a whole bunch of like different demand in the power system, like in the utility. Or like the worst thing can happen is like, um, when we have a different x or like different power reduction, it goes into the historical data, and then within this historical data, the learning curve can also be affected. So to demonstrate this case, we use this study in NYU Microgrid, which is in Manhattan. So NYU Microgrid has like total capacity of 13.4 megawatt, with like gas turbine generators and steam turbine generators, which supplies heat and electricity to most of the NYU buildings in Manhattan. And the microgrid is connected to the Con Edison network So in this microgrid, we conducted the study, and the very first thing to note here is like we have like many customers within the microgrid only. We have like tons of devices, as tons of air conditioners. Um, I don't remember the actual figure, but in reality, a utility has like thousands of customers. So to assume that like all of those customers can be attacked is bit unrealistic. So an attacker, it's of value that attacker rank the customers based on their value to the attack. So these customers are ranked using the Shapley value algorithm. So out of the total customers, only 30 customers are used for the further study. And then 30% customers, here we can see in the left hand side figure that the motive of the attacker is to change the incentive, demand response incentive sent to the customers. And the obviously the attacker here wants to increase the demand response incentive in such a way that the demand response, the utility now no more feels that the demand response is economical, right? It's economical to turn on the generator rather than ask the customers. So the motive of the attacker here is to increase the lambda in such a way. So here we see only 30% DR customers are used out of these ranked customers. And it is seen here that around 65, after 65 number of demand response events, the objective of the attack is achieved. So obviously we might achieve this target even on the lower number of DR events, but in that case we need a larger number of DR customers, which is a trade-off. So that's being the monetary effect on the smart grid. Let's say what can be the technical challenges in the smart grid. So for example, we are talking here about NYU microgrid. So in like the with the different values of changes or manipulation in the DR incentive, uh, the power demand also changes, right? For example, here at 11th hour demand response starts, and the 15th hour the demand response ends. So the with the uncompromised lambda, means uncompromised DR incentive, the nominal behavior of the customers, using the nominal behavior of the customers, the power demand would look like somewhere in between, like and when the attacker manages to manipulate the lambda by 2 times the value, the demand response increases, and but the overall demand of the overall demand of the microgrid decreases. So we can see there is a huge change in the nominal demand and the uh, demand caused due to the attack. So this difference in the nominal and the attack demand will incur a frequency excursion in the system. So just to note that frequency is a parameter in the power system which should be always 1 per unit. For example, in US it's 60 hertz. If it's above or below some of some certain predefined range, the relays, the power system relays will trigger, and we have to isolate the generation and or the substations. Otherwise, they will be like turn out, right? So here, once the power demand falls drastically at 11th hour, we have like the peak in the frequency. And when the frequency increases, let's say like 1.08 per unit, we need to forcefully cut out the generator from the microgrid or the system, right? So uh, due to this phenomenon, we can have the microgrid incurs a islanding, or also it can have the cascading effect of like different generators going off, going off one after the other, right? So in this case, like So these are the some of the vulnerabilities that we talked about, like in the device level for charging station and the process level for demand response. And I would like to talk about some defense scheme that we are currently exploring. So, for example, we are not here talking about the defense scheme that is on the device level. We realize that none of the defense scheme is 100% guarantee. And also, like, since these demand side cyber attacks are like more connected to the customers hygiene, this even the state of the art defense, most of the some of the customers even can't afford, or like they are unaware of it. So here we propose the concept of cyber insurance for like demand side devices like charging stations, which obviously can't avoid attack but saves from business loss. This is particularly important because like charging stations are like yet to foster in the energy business, right? So right now, cyber insurance market by industry vertical, they are more focused on the banking and the IT industry, and we have like a bunch of cyber insurance companies already in the market. But the penetration in the energy sector is like no, it's not significant yet. Like we even don't see in the uh, curve, right? So we propose Power Grid as an insurer for the devices like charging stations. So here we have like three labels. We have Power Grid on the top, and we have charging station in between, and Power Grid operated in the bottom, in the lower level. So how this frames is like the Power Grid will become an insurer for two reasons, right? So the very first reason is like the Power Grid do not want its internal data of charging stations to get out of the industry. And the second reason is like if Power Grid is an insurer, it already realizes that like attack in charging station also is the attack in the power system. So Power Grid here acts as not in profit seeking entity, but rather it acts as like um, insurance promoting agent, right? So for these two reasons we are using Power Grid as an insurer. So also we are working on this, and then like the initial results shows that like it's better for the charging station, more economical for the charging stations to go with like Power Grid as an insurer rather than other conventional insurance companies. So yeah, on conclusion, I would say demand side cyber attacks are mostly the function of customer cyber hygiene. And recently, up until recently, power grids would like leave charging stations and these air conditioners, high wattage devices unmonitored, right? They would simply treat them as a passive load, which would like create effects. Now they should realize that these high wattage devices are part of power system itself. So also the public data of the power grid and the like unmonitored charging stations, and those are like can cause issues, not only cause the privacy issues but also they can cause security issues in the power grid. And it all spurs a cyber consensus among power grid, this type of high wattage demand side devices, and the obviously the customer, right? So we need like it needs a business standard and like define the role and responsibilities within the charging framework or like the smart grid framework. And we also envision that cyber insurance could be a solution to foster like small green business like charging stations. Yeah, with this I conclude my presentation and happy to answer any questions if there are any questions.
Thank you. Thank you for your presentation. Are there any questions from the audience? You are free to unmute and ask your questions.
How's it going? My name is Christian Flores. I do have a question regarding, EV charging stations.
Mm-hmm.
Is it possible that the charging stations transmit and receive data from the servers?
Yeah, these days, like most of the charging stations within the network, let me just like show with that curve. So for example, here, right, we have EVCS companies in Manhattan. So there are like different couple of companies that have charging stations. So for example, Blink charging has its own network of like charging station servers, right? It collects the charging station data, like what time it charges and what is the power of that charging station, when it should turn on, when it should turn off type, and it should also define the method of payment, right? So yeah, they do communicate with the charging station servers.
Okay, so to lean off of that, since if it does transmit and receive data, doesn't that make also a possibility and a vulnerability attack for the actual EV itself, the electric vehicle? Since now that it's connected to the charging station and it's transmitting and receiving data, is there a possibility for a vulnerability attack within the actual electric vehicle?
Yeah, I completely agree with that point, right? There is a high chance that like um, for example, malware can transmit from charging station servers to the charging stations and to the electric vehicle that is charging, right? So there are like some of the research is going on in this domain, like the malware transmission among the vehicle charging station and the servers. Yeah, I do agree with that point.
Thank you for answering that question. I do have one more thing. Is that a possibility with that attack that all these EVs is kind of a new thing? It's coming into this cyber world. Is there a possibility that with that vulnerability attack, it can cause an electric vehicle to be manually override and possibility, endanger people who have electric vehicles? It can be a manual override. Someone else can control, that vehicle, through their computer or.
Yeah, I can see your point and your concern, right? So I completely agree that there is a possibility with this interconnection that the electric vehicle that is being charged um, can have like the security issues through the charging station. Moreover, right? So there are already existing like vulnerabilities that are already shown in the that are already surfaced, that uh, the payment method, the payment, the cards, the information of the payment method, that is like card systems or anything that is used by the EV users, those are like those are declassified in the using the attack. Yeah. So there are like also privacy concerns and the security concerns of the electric vehicle users with this integrated charging scheme. Yeah.
Thank you for answering the question.
Thank you. Uh, do I have something in chat?
Yes, you do.
Okay. So, okay. Where should I read from? 231, I guess, right? Okay. Like the idea of insurance. Thank you. We are working on it. Shared risk, shared benefit. Yeah, that's the concept. Leaving security to individuals will not lead to good outcomes. Yeah, I agree. We cannot like because it's the function of like the cyber hygiene of individual customers, right? It's very hard to monitor, and uh, yeah, we need to somehow work on the, let's say, charging station level rather than the customer level. I do agree with that point. uh, how are the developers, app developers, addressing this issue? So yeah, that's a very interesting question, right? So uh, once the vulnerabilities are like issued, for example, the charge point, right, that I said earlier, that's found vulnerable. So their vulnerability was like if the app, which is if the Wi-Fi which connects that app is compromised, he or she could she could already compromise the electric vehicle, because that app is connected to the vehicle, right? So for example, the charge point, once the vulnerability is addressed, the charge point like addressed that issue, and then like that is fixed. But this all of these issues are like coming one after the other, and then like like app developers and all of these developers, I would say, are like addressing issue based, right? So yet I would say like They are not yet into the addressing the whole cybersecurity issues of like the EV charging that includes the power system, but they are addressing on the issue based. I hope that this clarifies the answer. And then, are there companies that specialize in IoT security? Yeah, there are like, I do not have the exact answer, but I know some startups, they are like doing like IoT security, but I do not have a definitive answer for this one. Any more questions? Thank you.
All right. Well, thank you so much. Thank you everyone for joining us today. Hope you guys have a great rest of the week, and we will see you next month.
Okay. Thank you.
Thank you.
Thank you.
Thank you, Samrat. Appreciate it.
Thank
In the
you.
future.